folder of whatever name you want to. Maybe ensure that something which is you will be able to recollect later on. Let's say in my case, I have created a folder called lab assignment 3 with my name. Okay. So why do you want to create this? Once you create this lab assignment folder, I would have created another lab 3 subfolder. This lab 3 folder content is from the references that we have it from our professors. Okay. So he has one folder called maybe in IMP. No, not IMP. There is one folder where he has put all the VG sweep of MOSFET. Okay, maybe this is the one. Yeah, you see here, there is one folder called VG sweep. Okay, everybody, whoever has logged in to their OSHA portal would see this VG sweep folder. As a first step, you create your name underscore lab 3 or whatever, and then just copy this folder and paste it in your working folder. This is the first step. Okay. Just copy that and paste that VG sweep. Particularly, we are targeting VG sweep considering VD as 1 volt. Okay. VD as 1 volt. Take this folder. Okay. From this folder, within this lab assignment 3 folder, create one more folder as lab 3 or whatever. This is your reference folder. This is your actual folder that you are going to work on now. Here you will have you will create the the .scm file, and you will also run mesh.tdr. Everything you will do under this lab 3 folder. So what all you need to create the SD .scm files, as you know very well, this you have done multiple times previously also. You need not you. We need setup.tcad folder, correct? So we need setup.tcad folder, setup.tcad file. We need all the parameter files, for example, models.par, oxide.par, okay? And those files are present in this folder, VG sweep VD equal to 1. From this folder, you just copy. If you want, I can show once again. Okay. Let me go here. I'll create one more folder called lab 3 underscore 1. Okay. This is what we are working now. Forget lab 3 now. VG sweep VD equal to 1 is the folder which professor has created. Just take that folder as it is. Don't do anything. And create one empty folder called whatever it is, 3.1, 3.1, or whatever you want to name, you name it. Now,
in that VG script VD equal to 1, there is no setup file.
correct. I'm coming to that. I'm coming to that. Okay. So now, once you go into this folder, we need few important files. For example, we need the predefined .scm. Let's find where is .scm. dgt.scm. Here it is. Okay. And originally, you may or you may not have setup.tcad. It will be there in other folders. It's not a big problem. Just find setup.tcad, take this, and the parameter files. What are the parameter files? Oxide, model.par, silicon.par, and is there any other parameter file? You just check and confirm once again. No, right? Yeah, here it is. Aluminium.par, and then our CMD file. These are the files that I need to work now. Forget about all other files. Okay. You just take the parameter files along with the .cmd file and .scm file and setup file. Just right click, copy, go to my lab 3 underscore 1, paste. I'll pause here for 30 seconds. Do you have any questions or any, I mean, if are you not able to follow or anything like that? Let me know now. If it is okay, then I'll proceed because these are the simple things. We don't want to waste so much time here. Okay, fine. Now our activity will start here. Execution takes 20 to 30 minutes maximum, provided if we have created the .scm file correctly as per the requirement. Now, I have all the required files for me to execute. However, if I open this .scm, if I open this .scm file, you will see, okay, okay. In my case, I have created .scm for already for this project. In your case, you will see the .scm to be for 300 and 200 because that is what the professor has demonstrated during the experiment in the lab session. Now our job is to update this .scm for 105 bar or 105 into 90. That means we have length of 105 and width of 90 nm. Okay, this is the first step that we are going to do. Now for a moment I'll share my screen which I have written. Okay, and that will be useful. Okay, just a minute. Are you seeing my screen? Are you able to see the screen which
Yes,
I have
yes,
written
yes,
the
yes, yes, we can see.
okay, thanks Pradeep, thanks for confirming. Okay, now the assignment values are 105 nm in y direction, sorry, x direction, 90 nm in y direction. Okay, now what are the other known, before that I'll write here. Should I write it or whatever I have written, can I explain? What do you prefer?
You can explain, Chetan.
Okay, fine. So that would save time. Okay, maybe. Now, I hope this is little clear. You see, I am starting from point 0, 0. Okay, and the x direction, my end point is 105, comma 0. Okay, on the y direction, it is 0, comma 90. Here, this point, the top point, 0, comma 90. Okay, now question says my source and drain width is 30 nanometer. Length or width is given. One of the parameter is not given. So we assumed both to be 30 nanometer. Okay. So let's model that 30 nanometer. So 30 nanometer means now you see I have my rectangle, the P substrate. This is an NMOS, by the way. My P substrate is 105 by 90, within which 30 nm, 30 nm on both the sides are source and drain. So let's model that. Now, first point on the y-axis, you see here on the y-axis from 90 come down 30. That will be 0, comma 60. Correct? This is 0, comma 60. Same way, if you go towards right till 30, okay, because your width and length is 30. So that value will be 30, comma 60. Y-axis is 60, x-axis is 30. And at the top where it is on the at the top, if you see, it will be 30, comma 90. Are you getting this point? this one, 30 comma 90. Did you understand? Are there any questions here? 30 comma 90, is it clear?
Yes, yes, Chetan.
Okay, fine. From there, the channel length is 45 nm. Okay, you see the 30, from there channel length is 45 nm. If I say channel length 45 nm, you should also think that the gate length or the oxide length is also 45 nm. Okay, that I will show in the next when we are writing the .scms. I mean, when we are writing the drain gate and all, that I'll show you 45 nm how it is considered there. Now, from here 30 plus 45 will be 75. So this point becomes 75 comma 90. Y-axis is at 90. Y-axis is not changing. Only X direction we are changing. That's why 90 is remaining the constant. So from 75, again 30 mm. 30 mm thickness is the drain thickness. Sorry, source thickness. Sorry, drain thickness. If you add 75 plus 30, it will become 105.90. This is the point, end point. 105 comma 90. And at below it will be 105 comma 60. So this is n plus, this is n plus, this 30 60, 75 60. This is the channel length is 45. Above the channel, the thickness of the oxide layer is 2 nm. Okay, and the contacts I will match to the thickness which is 2 nm. So these are the contacts. One is source contact, drain contact. Now for the source and the drain contact, since my source total source length is 30 nm, while considering for the contacts, the usual process explained was 50% of this, which means 15 nm. 15 nm is the contact. Okay, 15 nm will be the length of this contact, and exactly at the middle of this, which is 7.5, I will place my electrode. 7.5 nm, I will place my electrode here. Exactly at 7.5, I'll have my electrode. Okay, and here exactly between 75 and 105, it will be like exactly what it will be like. From 75 to 105 is how much? Let's say from 105, you minus 15, this will be 90. Exactly at 90, this contact will be there, and 90 and 105, exactly half of it will be 97.5. Okay, are you clear? Now it should be seem simple, right? So this direction is 105. This is 90. Okay, this is 30. This is 30. This is 45. And this length is 30. And then this thickness is 2. This thickness is 5. And this entire thing is there, right? Each side it is 15, 15. The length of this is 15. 15. This is again 15. And exactly at the midpoint at 7.5, we have an electrode. Now coming to this gate. Okay, now gate will be, the gate contact will be already 2 mm of oxide thickness is there. Okay, above 90. 92 is the oxide thickness plus 5 mm, that means 97 nm. Is it clear? 90 is my rectangle, top level. On top of it, there is a 2 nanometer of oxide layer. On top of it, 5 nanometer of gate metal thickness is there. So it will become 97 mm. And then exactly at the middle, I have a gate electrode, which means 105 divided by 2 is 52.5. Exactly at 52.5, I have a gate electrode. Okay, this is exactly 15, right? 30 by 2 is 15. 30 minus 15 is 15. That means 105 minus 15 is 90. This is at 90. And electrode is at 97.5. This electrode is at 7.5. This, if you understand, the next steps are just writing the SCM file. Just take 1 minute to look into this diagram. If it is clear, then I'll go to this OSHA portal. I hope that is alive. Hello, you guys there?
Yes.
Yeah, yeah.
Any questions?
No, you can go ahead.
Okay, fine. Now, how I can share both? Which screen are you seeing now? Are you seeing my
It is
tab or are you
drawing
seeing
only.
my
It is
.scm
drawing
file?
only.
Huh?
Drawing only. Drawing only.
Drawing only you are seeing. Okay, now I want to share this .scm because without sharing I cannot edit it. Just give me 1 minute, okay? So I have to present this. Now, are you seeing the SCM file?
Yes.
Okay, very good. So let's proceed now. So first is P side, that is our P substrate, 0 to 105 and 0 to 90. This is our coordinates. Okay. Next, we will create N side 1, N side 2, that is source and drain. Source is from 0 to 30 X direction, 60 to 90 Y direction. Again, drain 75 to 105, which is like 30 nm, and then 60 to 90 because Y direction it is same. Only in the X direction we are moving. Any questions on source and drain?
No.
Okay, very good. Now oxide layer. Oxide layer, what I told, it is nothing but the channel length, right? From X, in the X axis, it is 45. That means from 30 till 75 is the gate length, correct? The channel length. And on the Y axis, 90 is my P substrate layer. On top of it, we are going 2 nanometer of oxide thickness. That is 90, from 90 to 92. Is it clear?
Yes.
Okay. Okay. Fine. Next, we are creating gate, source, and drain. When I told oxide, same length is applicable for the gate also. Do you agree or not? Same length, right? Because it is the gate is present just over the oxide. There is no difference. So X direction, there is no difference. So 30 to 75. On the Y direction, the gate is 5 mm, sorry, 5 nanometer. That 5 nanometer is nothing but from 92 to 97. Hey, by the way, somebody is recording or not?
I think you
Hello?
need to record. We don't have the option.
Uh, who is that lifesaver? Ah, Raja Garu. Okay. Thanks, buddy. Okay, fine. Next, we are done with the gate. Now let's go to the source. In the source, we know our source is 30 nanometer, but now we are creating the contacts, right? For which we are considering only half of the entire source length, which is in the X direction, 0 to 15. And in the Y direction, we are considering only 2 nanometer, same as the oxide thickness. Okay. Since I'm telling this once again, since there is no explicitly mentioned in the assignment for the source and drain contact lengths or contact parameters, we are taking same as oxide thickness. And this is what was demonstrated during the exercise as well, lab exercise as well. So the same thing we have taken. And creating the drain. Drain, again, it was, drain was, if you see here, 75 to 15. You see here, N side 2, it was 75 to 105, it was 30 nm. Now we want only 15 nm of the contact. That is why instead of 75, we are going with 90 to 105. Y direction remains the same, 90 to 92. Okay. So gate, source, drain is done, oxide is done. And what else? We are done with, come on, yeah. Don't waste my time. Okay. So we are done with gate, source, drain. Now we shall declare the contacts. This is the contact setting. That means this is where the actual your electrode will come and sit. Now, first for the gate, as I told you, for the gate, it is exactly at the center of the x-axis, isn't it? X-axis is 105 divided by 2 is 52.5. 52.5 is written as 0.0525. And on the y-axis, 90 plus 2 mm oxide thickness, 5 mm metal. At 97, we will have the gate electrode placed. Similarly, for source, we have 15 as the gate contact, out of which at the exact center, that is 7.5, that is written as 0075, 7.5, and y-axis is 2 mm, 2 nm above the 2 nm is the oxide thickness. Similar thickness we have considered for gate, I mean for the source contact. Exactly on above 92, we will have an electrode placed. Similarly, for the drain, which is 90 to 105, 15 nm it was, and 90 to 105, exactly the midpoint is 97.5, which is 0.0975. And on the y direction, it remains same 92. This is about contact declaration for gate, source, and drain.
Chetan, this source should be 0.075 or 0.0075?
0075. If you say 0.075, it will become 75 nanometer.
Okay.
0075 is because 7.5. Do you remember? Do you remember? I told you the N side is the source is 30 nanometer, correct? And half of that is 15 nanometer for the contact.
Yes, source is for 30 nanometer. Yes, upon
Correct.
that is
In
for
that
contact
15
15
nanometer, we
nanometer.
considered. In that 15, exactly at the midpoint, we will have the electrode, which is 7.5.
Right,
That 7.5, if you convert into micrometer
nanometer.
scale, it will be 0.0075 micro.
But we need to specify nanometer over here, not a micrometer, right?
Correct. 7.5 is nanometer.
Okay,
We are saying it in micrometer, not in nanometer. Okay.
okay.
Yeah. If I just write 7.5, then it becomes 7.5 micro in this case, which is not true. It will be like 7,500 nano or 7,500 nano. It is not correct, right? That's why we say 0.0075 micrometer or 7.5 nanometer. Anything is fine. Fine. Any other questions so far? Okay, done. We did that and wait here. We did this. And next is about the P side, N side, and doping concentration. For now, let's not touch anything. There will be place where we need to do all this circus during our the execution of doping concentration workbench. That time I will tell what we need to do. For now, let's focus on creating the proper SCM file. Okay. So for now, let's forget this. Let's go to the meshing strategies now. The thumb rule of meshing strategies, you know very well. Only one thing we need to ensure that the entire box, the entire MOSFET, whatever we have decided, it shall come under the box, the window that we are going to create. It's up to you. Any values you can write. Only thing you should ensure is we need to cover the entire box. So my X direction, I am starting it from -50. And Y also I'm starting it from -50 because my coordinates started from 0,0. Anything below 0,0 will be fine. If you ask me, can I take 10? Of course you can take 10. Nobody is stopping you. Okay. So you can take 10, you can take 20, you can take -100, whatever it is, but ensure that it will encompass your MOSFET. Now Y direction, the other coordinate of X direction, the total coordinate, the maximum value is 105. So I have taken 150. And the Y direction, it is 97.5. 97, considering electrode, all those things. So I have taken 120 to be more conservative. So my entire box is filled here. Okay. That's it I did. Now, the next point will be slightly little cautious we should be. That's it. On the multi boxes. Okay. Multi boxes, what we are trying to achieve is we are trying to ensure the entire source drain is covered here. From the source from the source to drain, the entire gate length is covered here. The catch here is you should have coordinates that are greater than your source drain width and length. Are you getting what I'm saying? Let me explain you. You see here X direction is I'm taking it from 25. Okay. So my gate length starts from 30 to 75, right? 30 to 75 is the gate length. I have taken below 30, that is 25. Below 30, that is 25 till 80. So 30 to 75 is the gate length. I have taken from 25 to 80. On the Y direction, if you see, from 90 at the top level, visualize this. Okay, visualize this. From 90, you go 30 mm below. That is your width of the source and drain. Below that, from that you should consider. Okay, from that you should consider. You can take 55 also. No problem. But you cannot take 60 or above. below 60 till 90, till your entire oxide layer. So I have taken another 5 points extra. So 60 to, or I mean, sorry, 50 to 95, 25 to 80. This is my meshing strategy, multi-box strategy. And 0.002, 0.001, this holds good for a given set of values. So this I don't intend to change. And after this, uh, just ensure what is your mesh TDR file. That is DGT underscore mesh, which of course no need to change right now. Later on, we need to change few things. For the save model here, meshing structure and DGT SDE and DGT mesh, we need to change it with some other parameter values for the SWB. But for the .scm file, as far as the .scm file is concerned, this is what you need to do. With this, that SCM file is completed. I'll give you 1 more minute time. If you have any questions, if you're not understood anything, please ask me. I can explain you. Meanwhile, I'll take one screenshot. Okay. If you're not clear on anything, please ask me. Not CMD. That is .SAT. .SAT is the output of the GUI mode. We are now not concentrating on the GUI mode. Okay. Yeah, through that's what we are doing now. We are editing each and every coordinate using .scm file. This is what is asked in assignment. Assignment is asked on .scm only. They are not asked in any other thing. GUI mode. Okay.
Chetan, I have a question.
Yes, go ahead.
Here, like multi boxes, you have declared, right? There we
Uh-huh.
can go up to 100. Can we give 100 there? You have
You
given
can give.
95.
You can give.
Okay.
Yes. Why not? You can give, but ensure
Mhm.
as finer it is, as good it will be. That's it.
Okay. Okay.
Okay. Just give me 30 seconds, friends. Oh, it's crazy, man. Okay, I didn't do anything, so I'll just close this. Okay, so now back to the original lab sessions that we did some time back. We just go to open in terminal. Remember one thing, when you copy these folders alone, okay, these folders alone, you will see there are no mesh.tdr file. That is what we are going to create now. Okay, so tcsh.
But Chetan, I think we
Yeah.
also need to do one changes in this parameters, right? Save
Huh?
model, and we need to take the values with the parameter, saving structure and meshing structure. So as it is mentioned, they need to be changed with the variables.
Correct. That is next step.
Okay.
So what you are saying is we will copy these .scm files there and CMD files there and then edit in that SWB. Okay.
Oh, okay. Okay.
Okay. For now, what we are ensuring is our design is proper or not. Okay. And that's why we spent the time creating .scm for the assignment values. Okay. TSC allappa. Yeah. So this you all know. SDE. Go to file. Open model. Ensure we are in lab3_1 folder and select .scm. And select dgt_scm. Open. You see here, right side, there are a lot of TDR files created. Okay, just close this fellow. Now what we need to do? We will do SDWise. Now, S visual.
Yes, device with that CMD, right? DD underscore D.
Yeah, DDR, that CMD. That CMD. Now, we need to see the waveform and we need to see our waveform, right? So open design.plt. So input is gate. Design.dsc input is gate. Voltage, x-axis. Output is at the drain current and it's a total current. To right y-axis. See, perfect waveform we got.
Which file you have opened?
Huh?
Which file you have opened?
Design.plt. Design.plt. PLT.
Okay.
This waveform shows our design is proper with the values that are expected. And for considering this as a base, now we are going to the next step, plotting the three values from the assignment. Okay. This activity is to ensure that our MOSFET is giving proper characteristics, ID versus VGS characteristics. If this waveform is not like this, something else, then we have messed up in .scm.
So what are all
Okay.
parameters you selected? You selected
Okay. For
AGSC
input,
drain.
yeah, for input, select gate,
Okay.
gate, and then voltage.
Outer voltage.
Yes, outer voltage, click on x-axis, to x-axis.
Okay.
And for again, select drain, total current to the right y-axis.
All right.
Okay, so this is done. Now, let's go back to our original folder again. Here in the lab3. Close this. In the same lab3 only, be here in this lab3_1. I'll create again new terminal. Again, TCSH. Again, setup dot setup.tcat.csh. Now, here from now on is the next assignment steps. We have to create the workbench file. Okay. For that, there is a command called swb. Just enter swb. It will open like this. Okay. Just click OK. It will open like this.
So in that new folder, you have just copied the setup file, no other things, right?
Which folder?
That lab3_1 you have created.
Yeah, under lab3_1, I have copied setup
Only
file, parameter files, and .cmd file.
No.
Okay.
This, new folder you have created, lab 3_1, right?
Yeah.
And there you copied all these parameter file also.
Yes. No, in the 3.1, I copied parameter files. That was
Okay.
our first step, right? When we
Parameter
started the
file,
project.
parameter files, and no. When we started, the one task we did, right? Device validation. And after that,
Uh-huh.
you created a new folder, and in this new folder, what you copied
Which new folder you are talking about?
from where, in which folder you started SWB?
I did not create any folder. I just create new terminal, not folder. New
Okay,
terminal.
so on the same folder you started SWB.
Exactly. That's it.
Okay.
Okay. Okay. Now please follow everybody. If you click on that SWB, this window will open. Click OK. This is what you will see. Now go to project, new, project, new, traditional project. Okay. Now save. When you click save, you will see something like this temp, and then you write forward slash and write what we are doing, MOSFET, right? Just write MOSFET. Okay, just write MOSFET and click OK. You will see here your temp and you have a MOSFET name. Are you seeing it?
Yes.
TMP and MOSFET. Now we need to add tools. Right click, add. Okay, go to tools. First tool we will add is this SDE, the first SDE. Select that SDE, click OK. Apply. Next, again click, add. Array.
You need to go to tool
Yeah,
and
yeah,
add.
yeah. Yes, device. So far, any questions?
No, Chetan, you can continue.
Okay, fine. So I hope you are following it, right?
Yes, yes.
Okay. Yeah, thank you, Shravani. Yeah, now, now remember, now this is where our activity starts off editing the things here. We need to input the command. Now, for SDE, we will copy our .scm file. For S device, we will copy .cmd file. This is the basic thing. Okay, just remember this. For SDE, we will copy the what file did I tell? .scm file. Okay, to do that, first let's go to this folder, the folder where we have our .scm, .cmd and all. Go to .dgt.scm. Okay, Control A, Control C. Right click. Come on. Yeah, yeah. Just a minute. Edit input commands. Now you paste it here. What we did, we just copied the .scm and pasted under edit command of SDE, right? And can somebody tell me there are the change name that we need to write here at n node at I think, if I'm
Yes.
not wrong. Can you confirm that?
N at the rate node.
N at the rate node n node at, right?
N at the rate node at the rate.
Yeah. Good. I remember that. So friends, see here on the .scm file, okay? Please scroll completely down. Okay, after our multi boxes that we have defined, right? We have something dgt underscore mesh, dgt underscore sde. There, you delete the dgt underscore sde, write this command n at node, n at node, node, again at with the same apostrophes. Don't delete apostrophes. If you delete, then it is gone. Okay. Again, the same thing we need to write for in the place of dgt underscore mesh. Okay, let's delete this. See, I meshed it. Okay, n at node, again at. Don't do any changes for now. For now, later we will do. For now, don't do any changes apart from these two. Okay, n at node at, n at node at. Save it. Save it. Close it. Okay. Similarly, now what we need to do? Dot command file dddscmd. Where is the dddscmd? Here, just open this. Okay. Control A, Control C. Go to S device now. Click on, right click on S device, edit input, click on edit input, go to commands, and paste here. This is where we need to do some number of changes. Okay. So here we need to be very careful. We need to do some critical changes and deletion, additions, everything. So first thing is we are not passing this parameter file here. This is not needed. Just delete that. Now whatever is there under quotes, you delete it. We will replace that with other commands. Okay. Okay. Just let it be this way. If I am not wrong, output is at log at, correct? Somebody confirm me this. Okay, grid is at TDR or what it is? Okay, fine. What about the plot? At TDR, okay. Let me see.
At TDR, DET at.
at TDR DAT.
At.
Yeah. Next is plot. This I remember.
Yeah, at plot at.
Okay. So first thing we changed, we deleted the parameter. Now we are editing grid plot current output with these values. Okay. You no need to by heart. This is already there in the training session. Just make a note somewhere so that you can write it as it is. Now, please pay attention here. First point in the experiment is we need to do VDS drive. VDS, drain versus gate source voltage with different VDS values, correct? With different VD values, drain voltage values. This is what we are going to do in this first experiment. For that, I will make the VD drain voltage as the parameter. If you scroll down in this .cmd file, you will see source, drain, gate voltages. Okay. Okay. Do not edit anything else except this parameter. The drain voltage equal to 1.00. There, what you should do, you just delete 1.00, write this at capital VD at. I'll pause here. Any questions? Let me know now. Because this is the first step for our first question of the experiment. We are asked to parameter the drain voltage for different gate source and ID current. That is what we are doing here now. Once we do this, we just save this. Any questions? We did not do anything else apart from renaming the renaming this grid plot current output. We deleted the parameter, we renamed this, and we went to drain section and did the parameter VD. That's it. And I will save and close. Now what I need to do? I need to add a parameter, right? So for that, I think somewhere here I need to click. No. No. From here, I think I can. Yes, it will be. Yeah, here it is. This one you should click the below the S device. So my parameter is, what is my parameter? VD, and I am doing it in linear value. My starting value is 0. My ending value is 1. Maximum values as per the assignment, I need 11. I'll click here. I'll get 0 to 1.0, 11 steps. I just click apply. Okay. And this is okay. And this you close it. Save it. Okay. We modeled VD 0 to 1.0 and we just click save and now select this entire thing. Once you select this, we need to run it. You just need to drag this fellow. No, nothing is happening. Just a minute. Sometimes this resolution will play with you. Okay, just have some patience. So just click on this run simulation. Okay, this is all okay. Just give okay. This you keep it aside. Let's see what is happening. Okay.
So that run selected nodes, right? That run icon.
Huh?
You need to click on run icon, right?
Yeah, we need to click this run blue color symbol.
Okay.
Yeah, once you click the blue color symbol, it will start running in the background.
It will show run project or home and click OK on that, right?
What?
So some another